Right. So are you able to see the screen? Bernoulli's theorem. Mechanical properties of fluids, session 10. Bernoulli's theorem. Yes, are you able to see the screen? Bernoulli's theorem.
Yes, sir.
Right. Now we'll start the lesson. So in this before going to Bernoulli's theorem, first we need to recall different energies. I think energies of flowing fluid we'll see first. After that we'll go for Bernoulli's theorem, because Bernoulli's theorem is relation between energies of a fluid flowing. So what are the energies that a fluid have? Energies of a flowing fluid. Energies of a flowing fluid. What are the energies that you can expect anybody? First one, let us say pressure energy. Already we discussed in the previous class. Pressure energy for a flowing fluid. Okay. Then the pressure energy, it is the energy possessed by a fluid or liquid by virtue of its pressure. What is pressure energy? It is the energy possessed by fluid by virtue of its pressure. Are you clear this point? This is already we discussed. By virtue of its pressure. Okay. So what is the equation for pressure energy? Have you remember? Pressure energy is equal to P into V. Have you remember? Pressure energy, P is the pressure and V is the volume of the fluid. Then pressure energy is equal to P into V. Okay. Then pressure energy per unit volume. Pressure energy per unit volume is equal to P. Have you remember? That is equal to static pressure. And pressure energy per unit mass. Pressure energy per unit mass, that is equal to PV by M. Then PV by M, what you can write? Let us say density rho, rho V. Then VV cancel. Then that is equal to P by rho. Have remember this? Pressure energy per unit mass, P by rho. Similarly, pressure energy per unit weight, that is equal to PV by weight mg. That is equal to PV by rho Vg, where m is rho V. Then P by rho z. What is the name that I said? Pressure energy per unit weight. Have remember? Pressure head. It is named as pressure head according to fluid mechanics. So this is about pressure energy, and this is the different types of pressure energies that we have. That means based on the per unit volume, per unit mass, per unit weight. Second type of energy for a fluid does we can expect potential energy. Second type of energy for a fluid is potential energy. Potential energy, either solid object or fluid object, it will possess. Okay. So what is potential energy? It is the energy possessed by fluid. It is the energy possessed by fluid by virtue of its position. By virtue of its position. Okay. So how to write this pressure potential energy? Normally, suppose let m be the mass of the fluid. M be the mass. Okay, it is at a height h. At height h. Okay. Then what is the potential energy of this fluid? P is equal to mgh. Do you agree this? P is equal to mgh. Are you able to following? Potential energy of the fluid at a height h. Yes or no? Suppose you can write in terms of density and volume, then I can say m is equal to density rho into volume v for a v volume of the fluid. Then what you can write? Rho v gh. Rho v gh. This is the potential energy of the fluid. Then potential energy Pe per unit volume. Pe per unit volume is equal to rho v gh divided by v. V cancel. That is equal to rho gh. What is this rho gh? Potential energy per unit volume of the fluid. Okay. Similarly, potential energy per unit mass. P per unit mass of the fluid. What is the value? P per unit mass mgh by m. That is equal to gh. Okay. Then P per unit weight. Potential energy per unit weight. P per unit weight is equal to mgh by weight mg. Then mg cancel, that is equal to h. Okay, this is the potential energy per unit weight of fluid or liquid. What is this h is called? Potential energy per unit weight. That is named as gravitational head. Gravitational head. Previously we defined pressure head. Now it is gravitational head. Are you able to following? Yes. Okay. So this is about second energy called potential energy. Next we can have third energy of fluid when it is flowing. What is that energy? Kinetic energy. Okay. Then third type of energy is kinetic energy of the fluid. Because it is flowing with certain velocity now, then kinetic energy of fluid. So what is this kinetic energy? The energy possessed by a fluid by virtue of its motion. The energy possessed by a fluid by virtue of its motion. The energy possessed by a fluid by virtue of its motion is called kinetic energy. Okay. Then how to define kinetic energy? Let us suppose let m be the mass of the fluid. M be the mass and small v, capital V is the volume, small v be the velocity of the fluid. Then its kinetic energy K is equal to half m v square. Half m v square. This is the kinetic energy possessed by the fluid because of its motion. Okay. Then you can write in terms of density. Then half m is you can write rho v into small v square. Okay, because m is equal to density into volume, rho into capital V. Okay, this is about kinetic energy. Then kinetic energy per unit volume, Ke per unit volume, that is equal to half rho v into small v square divided by capital V. Then capital V cancel. Half rho v square, half rho small v square. Half rho v square what? Kinetic energy per unit volume. Then Ke per unit mass, half mv square by m cancel, that is half v square. Okay. Then Ke per unit weight, yes, v square by 2. Ke per unit weight, that is equal to half mv square divided by mg. Then cancel, v square by 2g, Okay. So this is known as kinetic energy per unit weight. This is also called velocity head. Velocity head. Okay, before gravitational head, now velocity head. Velocity head is v square by 2g. So this is about three different energies that is possessed by fluid which is in motion. Okay. Are you clear up to this? Pressure energy, potential energy, and kinetic energy. Yes or no? Now we'll go for Bernoulli's theorem. Yes. Now we'll go for Bernoulli's theorem. Here again, once again, you can write Bernoulli's theorem. What is Bernoulli's theorem stating that? Actually, Bernoulli's theorem is based on the conservation of energy principle only. Bernoulli's theorem. It states that when statement I am telling first, statement of Bernoulli's theorem, when a non-viscous incompressible fluid, when a non-viscous, irrotational and incompressible, okay, that means ideal fluid, simply you can say. Non-viscous incompressible fluid flowing steadily, fluid flowing steadily, that means steady manner, flowing steadily, then the sum of the sum of the pressure energy, kinetic energy, and potential energy per unit volume of the fluid, per unit volume of the fluid, is equal to remains constant. Per unit volume of the fluid remains constant. Remains constant. Remains constant at all the points of the path of the flow. Remains constant at all points of path of fluid flow. Path of flow. So this is about statement. I repeat once again. When a non-viscous incompressible fluid flowing steadily, the sum of pressure energy, kinetic energy and potential energy per unit volume of the fluid remains constant at all points of path of fluid. At all points of path of fluid. Okay. So that means we know already what is pressure energy per unit volume, kinetic energy per unit volume, potential energy per unit volume. That we need to prove. Okay. So for that, we need to consider a situation. So within the tube, are you able to clear up to this? Let us consider a tube of non-uniform cross-section tube. In that fluid is flowing. That means let us say liquid. For example, water or whatever you can take. You can imagine this is the non-uniform cross-sectional tubular flow I have taken. Like this, you can observe here. So this is the starting cross section is high, at the ending it is low. So this is point number 1, this is point number 2 for the tube. Then with respect to horizontal level, let us consider a horizontal level. Let us consider a horizontal level. In that horizontal level, this is a horizontal level for suppose. So with respect to this horizontal level, this the height of this, let us suppose this point 1, this is point 2, 2 points, end points of the tube. Then this is let us say H1 height, this first end point, this end point is H2 height, and fluid is flowing like this. Okay, this is almost ideal fluid. Let us say pressure at the point 1 is P1, area of cross section is capital A1. Here pressure at point 2 is P2 and area of cross section is capital A2. Okay, it is very clear H1 is greater than H2 and A1 is greater than A2. Here, fluid entering at the point 1 is, let us say, with the speed V1. Fluid leaving at point 2 is, let us say, speed V2. Okay, V1 speed at point 1 and V2 speed at point 2. And pressure P1 is acting on the fluid from outside to into the fluid. Similarly, pressure P2. Actually, you can observe pressure P1 is along the fluid direction, whereas the pressure P2 acting opposite to the fluid flow direction. Okay, from outside to inside, always it will act pressure with respect to the tube. So that V1 is the direction and P1 along the same, whereas P2 and V2 opposite direction. This is the point you have to remember. Okay, and let us consider, let a small m be the mass of the fluid which is coming. Okay, let small m be the mass of fluid or mass of liquid. Okay, now in this scenario, we need to prove the statement what is given by Bernoulli. So for that we need to calculate one by one. So let density of the fluid is rho, because incompressible no, density will be same here and here. Okay, rho will be same. So then mass we can write mass of the fluid in a dt interval of time, m is equal to density into volume. Then volume I can write at point 1, density into volume, what you can write area of cross section into V1 speed V1 dt. Density into volume. Are you clear? This mass is equal to rho v. Rho v is equal to rho a1 v1 dt. This v1 is speed for a dt interval of time. Are you clear? This rho v is equal to rho a1 v1 dt. How it came? Yes or no? Or one more step you can write rho a1 into what you should write exactly? Rho a1 into, let us say, some x1 length, because volume you can write a1 into x1. Then what I can write rho 1 a1 into x1 v1 into dt interval of time, because x1 by dt is v1 na, then x1 is equal to v1 dt. Then let us say small amount of mass in a dt interval of time which is flowing is rho a1 v1 dt. Okay, right. Then this mass is entering with a speed v1 at a point 1. Then the work done on the fluid due to pressure energy, you can write at point 1. Work done is equal to what you can write normally, work done by pressure P into V. P into V directly I can write. Okay, because force into displacement, everything is boils down into P into V. That P means P1 into V. V means what you can say, P1 into V. V means A1 V1 dt. Volume means what? A1 V1 dt now. Then work done at point 1 on the fluid is P1 A1 V1 dt. This is equation number 1. Okay. This is actually here work is positive because force and displacement along the same direction. Pressure and fluid flow along the same direction. This is at point 1. Then work done on the fluid at point 2. And work done on the fluid at a point 2 is P2 into V. Then what you can write? So actually here P2 into A2 V2 dt. P2 into A2 V2 dt, that will come negative. Why? Because say V2 and P2 opposite direction, or force into displacement opposite direction. Say the fluid is coming out, pressure is acting inwards. So that minus P2 A2 into V2 into dt. Are you clear this equation? Equation number 2? Yes or no?
Sir,
Right. Then the total work due to pressure is, let us say WP pressure, work done due to pressure is P1 A1 V1 is speed V1 dt minus P2 A2 V2 dt. Equation number 3. Okay. Then there is a height difference also taken H1 to H2, because H1 is greater than H2 also I said. Then if a height difference is there, then from high altitude to low altitude liquid is coming. Then there is a work done due to gravitational force. Then we can write work done by gravity. Next is work done by gravity or gravitational force. Then what is that work done by gravity? Wg is equal to mg or mgh. That means mg into h1 minus h2. Are you clear this? Work done by gravity,
Sir.
mg into h1 minus h2. That means from h1 height to h2 height it is reached. Next point, work done by pressure over work done by gravity over. Then total work on the fluid is equal to W pressure plus Wg gravity. That is equal to P1 A1 V1 dt minus P2 A2 V2 dt plus mg h1 minus h2. mg h1 minus h2. This is the total work. Again, from work energy theorem, have you remember work energy theorem? From work energy theorem, work done by external force is equal to change in kinetic energy of the fluid. Work done by external force is equal to change in kinetic energy of the fluid or solid, change in Ke. So first, what is the change in kinetic energy? Initial velocity v1, final velocity v2. Then delta Ke is the change in kinetic energy is equal to half m v2 square minus half m v1 square. Okay. So final kinetic energy minus initial kinetic energy, half m v2 square minus half m v1 square. Okay. Right. Then you can equate work energy theorem. P1 A1 V1 dt minus P2 A2 V2 dt plus mg into h1 minus h2 is equal to half m v2 square minus v1 square. So this is about by using work energy theorem. Okay. Then you can divide with unit volume. Okay. Then what is the volume value? So you can divide with mass. Okay. Both sides. What is the mass value? Mass m is equal to density rho into volume. That is the density rho into volume means area into velocity v into dt. Rho a v dt. Then at the first side m1 is equal to rho a1 v1 dt. Other side m2. That means rho a2 v2 dt because of velocity changing. So you can divide with mass both sides. Then what you can write? P1 A1 V1 dt divided by rho A1 V1 dt minus P2 A2 V2 dt divided by rho A2 V2 dt plus mg by m mass. Now here m formula I written h1 minus h2 is equal to half m into v2 square minus v1 square by m. Divide both sides with m. Okay. Then here what you can write? This rho a1 v1 dt, a1 v1 dt cancel. Here a2 v2 dt, a2 v2 dt cancel. M cancel. Here mm cancel. Then what is remaining? P1 by rho minus P2 by rho plus g into h1 minus h2 is equal to half into v2 square minus v1 square. Half into v2 square minus v1 square. Okay. Then you can separate step by step. First P1 by rho plus GH1. This V1 square you can take left side, then plus minus half V1 square it will become plus half V1 square. Okay, is equal to this P2 by rho you can take right side, P2 by rho minus GH2 will become plus GH2 plus half V2 square. Okay, then rho you can multiply, that put LCM, then P1 plus rho GH1 plus half rho V1 square is equal to P2 that divided by rho P2 plus rho GH2, V2 plus rho GH2 plus half rho V2 square divided by rho. Both sides rho cancel. Then the remaining is P1 plus rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V2 square. Are you clear this equation? P1 plus rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V2 square. What is this P1? Pressure energy per unit volume. Pressure energy per unit volume. Unit volume. What is rho GH1? Potential energy per unit volume. Potential energy per unit volume. I remember initially I defined all these things. PE per unit volume. What is this half rho V1 square? Kinetic energy per unit volume. Kinetic energy per unit volume of fluid. Then what it is stating that P1 plus rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V2 square. From this we can say directly P plus rho GH plus half rho V square is equal to constant. P plus rho GH plus half rho V square is equal to constant. Are you understood this equation? This is Bernoulli's theorem. P plus rho GH plus half rho V square is equal to constant. That means the statement what I said, when an incompressible non-viscous fluid flows steadily, the sum of the pressure energy, kinetic energy and potential energy per unit volume of the fluid remains constant at all points of the path of the flow. That means at point 1, at point 2, we proved that at starting point and ending point. Okay, are you able to clear this point? At point 1, at point 2, we proved that the algebraic sum of the pressure energy, kinetic energy and potential energy per unit volume of the fluid remains constant. Yes or no?
Sir.
Yes, very good. So from this it is confirmed that we proved that Bernoulli's theorem. So that P plus rho GH plus half rho V square is equal to constant. Okay. So just I can recall once again. So because this is a big proof, so that you can understood where we started, where we ended, we can see once again. See statement you understood already. For that, let us consider 2 points of the tubular flow. In that initial point 1, where speed V1, pressure P1, area of cross section A1. This point 1 is at a height H1 with respect to horizontal level, and another point end point, speed V2, pressure P2, area of cross section A2, it is H2, and H1 is clearly greater than H2. And let M be the mass of the fluid. M is equal to what I written, density into volume. That is rho into area into x, let us say, length. Then that rho A into V dt. That means x displacement you can write velocity into time. That is for a dt interval of time, the mass flowing is m, small m, then rho A1 V1 dt. Same, by conservation of mass, same amount of mass should come out. That is equal to rho A2 V2, rho A2 V2 dt. That means m is equal to rho A1 V1 dt. That should be is equal to rho A2 V2 dt by conservation of mass. Then first you can calculate work done by pressure on the fluid. That is P1 into V. That is P1 into A1 V1 dt. Similarly, at point number 2, P2V. That is P2 A2 V2 dt. But here negative way because here pressure and velocity opposite direction because fluid coming out. Then total work is work done by pressure P1 A1 V1 dt minus P2 A2 V2 dt. Similarly, work done by gravity Wg is equal to mgh. But mg height difference h1 minus h2. That is work done by gravitational force. So total work is equal to W pressure plus W gravity. So that is the total value written. P1 A1 V1 dt minus P2 A2 V2 dt plus mg into h1 minus h2. Then by using work energy theorem for the fluid, work done by external force should be is equal to change in kinetic energy of the fluid. The change in kinetic energy I taken delta Ke. What is this delta K exactly? K2 minus K1. So what is K2? Half m V2 square, where velocity V2, final velocity. What is K1? Half m V1 square. So the delta K is equal to final kinetic energy of fluid minus initial kinetic energy. Half m V2 square minus half m V1 square. Then we equated work energy theorem. Then work done by force should be equal to change in kinetic energy. That is P1 A1 V1 dt minus P2 A2 V2 dt plus mg H1 minus H2 is equal to half m V2 square minus V1 square. Then we divide with the mass both sides. Okay, then mass value we know rho A1 V1 dt or rho A2 V2 dt or m. So all the m value you can divide left side and right side. Then finally you will get P1 by rho minus P2 by rho plus g into H1 minus H2 is equal to half V2 square minus V1 square. From this rho we have LCM we have done. After that we will get P1 plus rho g H1 plus half rho V1 square is equal to P2 plus rho g H2 plus half rho V2 square. So what is this P1? Pressure energy per unit volume, and rho g H1 is potential energy per unit volume, and half rho V1 square is kinetic energy per unit volume. Then we understood that at point 1, initial point of the tubular flow, and final point, the sum of the pressure energy plus potential energy plus kinetic energy per unit volume of the fluid is equal to sum of the pressure energy plus potential energy plus kinetic energy of the fluid at per unit volume is equal. Then we can write in general statement P plus rho g H plus half rho V square is equal to constant. Okay, hence it is proved the Bernoulli's theorem. Actually, Bernoulli's theorem conclusion is what? Based on which principle we have proved this? By conservation of energy principle only. By conservation of energy. That means inherently Bernoulli's theorem stating conservation of energy principle. Okay, right. Are you clear this up to? Yes or no?
Yes, sir.
Right. Suppose if the height difference H1 minus H2 is there, no? That height is same height. Suppose if H1 is equal to H2, that means the tube is at the same horizontal level. Okay. Then what happens? H1 minus H2 is equal to 0. That means H1 is equal to H2. H1 is equal to H2. That means if there is no height difference. Okay. Then in that case, the work done by potential energy is 0. That means this rho g H will become 0. Okay. Then what is the remaining? P plus half rho V square. P plus half rho V square is equal to constant. If the tube is at the same height, then work done by gravitational force is 0. Then only work done by the pressure will give the change in kinetic energy. That is P plus half rho V square is equal to constant. From this, what you can say? P plus half rho V square. That means P1 plus half rho V1 square is equal to P1
P2
plus P1 plus half rho V1 square is equal to P2 plus half rho V2 square.
sir.
Okay, from this we can understood. Suppose at any point, if a pressure decreases, then velocity of the fluid increases. Or vice versa, at any point of the fluid path, if the velocity increases, then the pressure definitely decreases. The velocity of the fluid flow increases, then pressure will be decreased. What does it mean? Suppose if the fluid is flowing from high pressure to low pressure, then what happens when the fluid is flowing from high pressure to low pressure? Okay, then what happens? The velocity of the fluid will be increases. Velocity of the fluid will be increases. That means change in pressure will give the change in kinetic energy. Directly you can write. Okay, so that is one application. Whenever the pressure will be, that means whenever fluid will be increases its speed at certain point, then at the corresponding point the pressure slowly decreases. Okay, that means pressure difference will create the change in kinetic energy. If you remove the potential energy, H1 minus H2 is equal to 0. Okay, So this type of phenomena, you can say so many applications is there. Okay, that pressure difference will make the change in velocity that we can see later. Okay, so this is about today's lesson. Thank you, one and all. Time up. Have a nice day. Okay,
Thank you, sir.
thank you.
Sir,
Yes,
sir, what is your Monday's NEET test question, sir?
Monday need test portion. Don't worry, you have time now.
Sir, but I'm asking for
Yeah,
studies, sir. So it will be.
fluid dynamics will definitely fluid dynamics only it will be there.
Okay, sir.
Okay, right.
Okay.
Thank you.